Then give me just a second. Okay. Okay, good morning. Let's start a little bit slow. Let me just give you what the overview is for the rest of the semester. So this week, we'll continue talking about this 1D scenarios, stationary states, and we'll see, we have to go through a lot of them, but it's nice because they show us different physical phenomena. Then we'll spend a couple of weeks talking about spin and the generalization in spin that also allows us to talk about rotations in 3D. And then from there, we can talk about the hydrogen atom. And this is kind of the mandatory stuff in the course. And then I should have many weeks left to talk about uncertainty. So how do we model uncertainty about the evolution or the state, also the uncertainty principle and so on. And if we have time after, we'll talk about foundations. And I hope at least in the last week that should not be in the exam, that I can talk about foundations of quantum physics. That's kind of the rough plan for what's left. So we saw that there are some possibilities just for a bound interaction zone. I'll go into this in a bit more detail. With two left to do, the reflecting states and the scattering states. And then we need to look at what's in particular inside this interaction region, and we'll look at the two simplest cases, which tell us, one, what's the recipe to solve this in general, and two, what kind of funny phenomena we can already observe that are very particularly quantum. We don't see this with classical particles. So that's the plan. So let's just recap where we were. And we have Hamiltonians of this form, p squared over 2 mass, v of x. And we look at stationary states for bounded interaction zones, which means that we think of a small x like this. And, oh, yeah, thank you. And we look at potentials of this form, where we have some potential on the left, then we don't know what happens, then we have some potential on the right. This is the interaction zone. And we saw that what we do is we solve the solution for the flat case, and then we have to glue it together depending on what's happening in the middle, depending on some continuity conditions. So for the flat zones, remember, these are energy eigenstates, so we have two options: either the energy is higher than the potential or lower. And this was that for E smaller than some, so this is flat potential zone. In these cases, X, so that this general solution is of this form. So this corresponds to a wave moving in this direction, and this corresponds to a wave moving to the left. Yeah. And this K was given by E minus V0. And for smaller than V0, remember, we're just solving the Schrödinger equation for stationary states, so then you get real exponentials, E dx plus d E minus dx, which corresponds to a wavelength and something like this. And B is the same thing. Except we flip the sign here, so V0 minus B, so it's still positive. Okay, and then what were the continuity conditions? So if you remember, the wave function must always be positive. Sorry, must always be continuous. Let me do it here. So that then we keep this up. What happened to everything? Okay. So we saw the wave function has to be continuous. If the potential is finite, then the derivative is continuous. If the potential is continuous, then the second derivative in order to x is continuous. Then we saw we need to normalize it. And then we saw that the energy must be larger than the minimum of the potential. So one, this must always be continuous. V of x. And this is the x derivative, must be continuous. If v of x is continuous, and the second derivative is continuous, and you must be able to normalize it. This is all for the and finally we saw that the average energy of the particle must be larger than the minimum of the potential, right? So this is all that we did. And then we looked at the first case, which was the bound state. Which was when V of x on both sides is less than the energy. So we're looking at, this is both a property of the setting, so whatever potential you have there, and also of what particle you shoot in. So sorry, the potential is smaller than the energy, so the energy should be down here. And if I have, for example, it left like this, and we don't know what happens. Be right here. The energy of my particle is down here. Well, one thing we know is that this potential must come below this energy, otherwise this would not be allowed. But inside here, anything could happen. And then we saw that the wave function in this case is just decreasing in both directions. Here we are. So now note that this is kind of units of energy, but now I'll just write the wave function and it looked like chook. Something happens and then it decreases a bit faster, right? And here inside, it will depend on what's inside this box. So this was x, some kind of at x, and C write x. Minus. Okay, so we have two other cases too. And I can already tell you that this is already surprising because classically, if your potential is higher than the energy that you have, there's no chance you'll be seen outside of this region. So can imagine that you're stuck inside the well, but you'll have energy to jump so far, you'll never be able to be here. But quantumly, there's some probability non-zero, which it decays exponentially with the distance, but there's still some probability of finding it outside this box. So that's already kind of special. So then we look at scattering states, and this is when the energy of the state is larger than both VL and VR. So in this case, we are on the left and on the right in this solution. So we have an exponential, sum of exponentials on both ways. So again, do the potential in green. So we have something flat here, then maybe something happens, we don't know, and then it can be something else. So now we know that in both sides, we can have a wave function coming here, a wave function reflected, a wave function coming here, and a wave function reflected. But the momentum k depends on the potential, so this is a bit different. So let me just write what we have. So in general, we have x. So we have a, e, I, k, l, x plus b minus I, k, l, x. X smaller than this limit. And then we have right x right x, or x larger than the other limit, right? And now all of these constants will depend on what's happening here in the middle. This case are given by this. This case are given by this, so they are different depending on the potential on the left and on the right. But now, the part that's important is that normally we are interested in solutions where this wave on the right coming from the right is zero. Okay, this is, now look, this is a general solution. Okay. Now we are interested in general in cases where this equals zero. And why is that? Because then we can think of this as a stationary solution for the following scenario. I have a source of particles here. So I'm shooting electrons from this side, right? They come, here they come incoming. Some of them are reflected. Something happens to them here and some of them are transmitted. And this is very common, like I want to characterize some material, we'll see later how. So I just shoot electrons there, right? And this stationary solution will give me an approximation for what happens after I've been shooting them for a long time. So we're not interested in the case of like shooting them from both sides, but we're interested in this, like, and then you'll see in the tutorial also that we can ask questions like, what percentage or what's the difference in amplitude between incoming and reflected and transmitted. And this is something that we will care about. Okay. So in general, we will care about solutions of this form. The other thing that we will do a lot, and I'll explain it again later, is to divide everything by A. Okay, this doesn't matter. We divide everything by A so that here we have 1. And then the A we worry about later, or we will not worry about at all in the class. The A will be given by the normalization. So in general, we'll just be looking at E to IKL plus B something, and on the other side, just C something. Again, it's not cheating, it's just saying, well, I have a constant here, I just divide everything by this constant, and I'll worry about this constant given, depending on the normalization. We'll see specific examples. So there's only one case left to see. Maybe I'll do it up there. So this is called reflecting states. And this is the case where the energy is kind of in the middle. Then this is V of x. And your energy is something here in the middle. And remember the exact setting as before, you're just shooting a particle with lower energy at it. So let's suppose that you have your the L smaller. Then something happens, we don't know. And then we have the VR higher. So then what we know? Well, we know on the right, again, there's two possible options. Either it will decrease with x, or it will increase with x. But if it decreases in x, then it will diverge, right? This is not, this is unphysical. Because then you cannot normalize it. So then we discard this option. So then here it must decrease. On the left, it's going to be the same thing, the incoming and the reflected. And the difference to the RS solution is that there's no, this is not like a wave moving there. It just means that with some probability you can find it here, but this probability decreases with x. So then we have what? Overall, we have x, a, eikx plus b minus eikx more than xl, and c right. And in the middle, we don't know what happens, right? Okay, and these are called reflected states because, you know, most of the wave is really going to end up being reflected. You will work on the tutorial about looking at the ratios between A and B in this case. Okay. So that's like the overall picture. Now we zoom in and we need to see what's happening here in the interaction zone. So the simplest case is we just, this interaction zone is nothing. There's just a step potential. So let me write it down. And now we look at explicit. Interaction zones. And this is the simplest. And this is what? Well, x. This is v of x being simply chuk, chuk, chuk. Okay, here's, I mean, now what we do is be clever about our coordinate system. So we put here the 0 so that we don't have to always be writing things. Be writing a VL. This VR is just V0. And then we can put the 0 of our horizontal axis wherever we want. So we just put it here. Okay. Yes, remember, this is a choice always. So we could put this x0 to be something else, but then just inviting trouble. It will be the same equation, just a bit more annoying to solve. So note that this is not continuous here. So you cannot expect the second derivative to be continuous, but everything else should still be okay. So now we have two options, right? either the energy of the particle is higher than V0 or it's lower than V0. It cannot be lower than 0 because then we violate the last condition, right? The energy of the particle must be always higher than a minimum of the potential. Okay, so we have these two options, and let's look at this one first. And this is useful now because we see how to glue the two solutions. So that's this situation here, right? It's exactly this, except we got rid of this thing in the middle. So we have this solution, but now with x smaller than 0, and here x larger than 0. And now we're going to apply all the continuity conditions to see how to find these coefficients a, b, and c. First, we take a equals 1. Okay, so we take this one equals 1. As I said before, because this will come from the normalization at the end, we don't worry about it. Okay, so first we have at x equals 0, what we have. Well, first, psi of x at x equals 0 must be continuous, which means that this must be equal to this, right? So you have e to I k x is 0 plus b e to minus I k 0 equals what's on the right, c e to minus b 0. Yeah. So from here, we get 1 plus b equals c. No? From the second one, maybe I write it here. So now we need that also. The first derivative must be continuous. So then we just take the derivative of this. So if you take the derivative of x, you get the factor of ik here, minus ik there, minus b there. So you get ik e to ik 0 minus ik c ik 0 equals minus c b e to minus b times 0. To write this a bit neater, you get ik minus b would be equals c. So now, look, how many variables do we have? We only have 2 variables, b and c, and we have 2 equations. And this is going to be the trick always. The trick, like the recipe always. So we have 2 equations, 2 variables, k and b are known. We assume that they are known because we know v0. So then we solve this. And remember, this is all up to normalization. We don't care about this for now. So I assume you know how to solve a linear system of equations. We will anyway probably, no, we will not ask you in the exam to do it. I mean, this one, maybe we will, but this is the simplest case. So what we get is b equals ik plus small b, ik minus small b. You can try to do it at home. E 0 minus e. Okay, and see, this kind of one of the last times we'll do it explicitly, the whole thing. Ik minus b. This is 2i square root of e square root of e minus v0 minus e. it's not super important. Okay, so first of all, so the thing we do now is, in general, we follow the maths, we find all these coefficients, and then I try to find qualitative ways to interpret what's going on here and ask the right questions. One thing that's nice to see here, just from looking there, is that if you look at the absolute value of B, it's going to be 1, right? Because this is B plus IK minus B plus IK. The two numbers here have the same norm. So if you divide them, same, which is good because A also had, we picked A to be 1. So it's like the incoming and the reflecting is have the same amplitude overall. Good. And another thing you can see is like, oh, what's the probability of finding the particle at some x that's larger than 0 for this particle? And that's going to be given, well, we take the wave function here. So it's C, and now it's squared. So we get C squared e to minus bx times 2 from the square. So we can see already that it decreases exponentially. And the other thing you can see here, because look, maybe it's not very obvious, but if you look in the denominator, we have here V0 minus E, and no equivalent thing on top. So if you make this potential much higher than the energy of the particle, then this thing, this time is going to be very large, which means that the whole thing is going to be very small. So then C is very, very small. Okay. So that's kind of the kind of insights, which in this case are not very surprising. So is it okay? Is it clear so far? In the exam, by the way, I might ask you to write the continuity conditions for a certain case. But in general, we will not ask you to then solve it, because this one was simple, but you'll see that very soon you have 4 variables and 4 linear equations. And I mean, the point of knowing if you know quantum mechanics is not to know if you can solve. It's not a linear algebra course, right? So that was one case. And now the next case, which is also not a lot of fun, the ones after will start to be more fun. So the other case was if B scattering. Now we have a scattering case or state, which is when E is larger than B0. Meaning we are in this situation. Here's the E. So a particle has very high energy, but the question is, does it still feel the potential, right? So we know that it does, that, you know, here we have something in common, and that here the wavelength, so the K changes depending on the potential, right? And once more, we're not interested in solutions that with the other wave coming this way, we're just interested in this one. So then we have what? X KLX plus B minus I X small equal to 0. C E X plus D okay. And once again, by the way, you can try to do as homework what happens in the limit case where E is exactly equal to B0. So again, we're interested in this case where this is 0 and we set A to be 1. And now we have again two continuity conditions, so we just do it. So f of x 0 must be continuous. From here, and now I'll just do, so replace this with x equals 0, so we get 1 plus b equals c. We don't have d. And if the first derivative of this condition is 0, then we get, so now we're going to get all the i's canceling out. So we get, I'll just do it, AKL times 1 times 1 again plus b minus AKL times 1 equals AKLC times 1. So get that C equals L over KB. Okay. So again, from here, we have two equations, two variables, nothing to do with it. We can just write the explicit solutions. I'll just write them here for completeness. But this is not the interesting case that we want to look at. So these KL minus K right, KL plus K right, which is zero. Right. 2 square root of E over so in the class, in the tutorial, you will now compare these coefficients A, B, and C. Well, A is 1, but B and C. But you can see already that B squared is no longer going to be a 1. So some of the wave is incoming, but some of it will be reflected, but not to the same amplitude, because some of it will be transmitted. So that's, so far it looks simple, but now let's make it a little bit more complicated, and now we start seeing interesting phenomena. And this is now, you'd think that now we're just gluing solutions, but what we'll do, we'll have some surprising consequences. So square barrier. We have number 1, step potential, this is number 2. Okay, so this is when now we make our barrier non-trivial, and it goes like this. And now, once again, we have two options. Either the energy is higher than this V0 or it's lower. V of x. Zero. This is an L. And in both cases, we see surprising things. So let's see the first one is tunneling. This is the famous quantum tunneling. This is when E is smaller than P0. So what happens in this case? What's the general solution? We can just write it down. We can just draw it. So here we have something is coming from this side. Here the same with the same K. Chuka, chuka, chuka. We can even have this one, even though we'll dismiss this later. And then in the middle, the wave function must be decaying, but except that now the difference is that on the other side is also valid because it will not diverge. We're only doing it for some finite period here. Right, so this was the just a solution for this flat area we have. Okay, X. And we have C EBX. Then we have some like E, so we jump to F, IKX. So this is for X smaller than 0. X in the box. X larger than 0. Right. And now again, we're interested in the case where this is 0, just meaning no wave incoming from the right infinity, and this one is 1. Okay. In the case in the B's, you know how to calculate them. So now I will just write what the conditions are. Okay. So we have 2 points where we need to glue things. One is at 0 and one is at L, right? So at 0, the wave function must be continuous. And this gives us again 1 plus B plus C plus D. This one must be the same as this. The first derivative must be continuous, and this will give us similar to the previous case. IK 1 minus B plus B D. Wait, I'm just taking the first derivative and then replacing with x equals 0, then simplifying a bit. So now we have 2, but we have 4 variables to work out. So we have B, C, D, and F. So we need 2 more, which means we need to look at f of x at the other point. And this gives us another equation, which will be just gluing this solution in this. So C, B, E minus B, L. So x equals L equals F, E, I, K, L. And then we still have 1 more, which is for the derivative in this zone, which let me write it here. So this is B, C into BL minus D, E minus BL equals IKF. So this comes from the last one. Okay. So this looks pretty horrible. Yeah.
Like a little bit above, like the equation.
This?
No, above that's
Wait, sorry.
Why there is this D term? Like in the picture would be like the.
It's this. Yeah. Yeah. I mean, we cannot rule it out as in physical just yet because it's not like we let this go on for plus infinity. Yeah. It's still inside a bounded region. Yeah. So we might still something coming out of here, and we will see something.
It just looks like there's something coming from the right and then going into the barrier from the right.
Yes.
Okay.
Yeah. Yeah. It looks like this, but.
And we are like, and did you say G is equal to 0 there?
Yeah, I did set J. Okay, so.
And that was that like it comes something from right?
This would be coming something for the right, yes. But look, this thing is not coming from anywhere, right? This is not a wave. If we evolve in time, it's not a wave that is moving. It is anti-intuitive. But look, one way to look at it, maybe more exactly, be well, general solutions. You can always see them as a superposition of. Pick whatever terms you want, plus, for example, something going like this. Here, like this. Right, you can always write the general solution and then work out. If I was writing the general solution, then I would definitely, I would still keep the J here. And now the thing is, these are all the conditions we have. We have 4 conditions, 6 variables, 4 conditions plus 1 for the normalization. So we still have 1 free parameter, which is a G, and I set that 1 to 0. Right, just to reflect different physical scenarios. But yeah, I know it does look weird. Yeah.
Last equation is both for x greater than 0 or x greater than 9. On the top again.
Oh, L, yeah, this should be L. Thank you. Yeah. Yeah, so. So now, if you want now the exact solution, we have 4 equations, 4 variables. You plug them into a computer. It's not hard to solve. You can even solve them by hand if you want. Or you can just ask specific questions, which is what we'll be doing now. Right. So in particular, we're going to look at the transmission rate. So now one question one can ask is going to be, well, what's the coefficient f of the wave that is transmitted? So the one that survived this barrier versus the incoming one. And I will tell you later some application of this. So again, we could have all the coefficients now, but we'll just ask about some specific questions. Transmission. And we talk more about this thing in the tutorial as well. So T is F squared. It's really the transmitted wave amplitude divided by the incoming wave. This one we set to 1 for now. This one is 1. So then we just need the f squared, which is known. We don't have the explicit form, but I'll give you now the explicit form for this t. And you just have to trust me that it's this. So in fact, it's 1 over t is given by this 1 plus n squared minus e. And now the hyperbolic sine square of b times L. Okay. So it looks pretty horrible. Let's see what we can tell from this. So first, let's plot this part here. Let me just plot this part here. So if this is x and this hyperbolic sine of x, then it looks 1, 1. It looks a little bit like this. So by which I mean that in this zone, it looks like, it looks more or less like x squared, and this, and for large x, it looks a bit more like some exponential function. Yep. The nice thing is that, again, these are things that you can verify experimentally. But I don't know, you shoot 1,000 particles and see how many of them arrive on the other side. Now, in order to have some idea of what to make, of what to take away as a lesson from this quantity, let's again look at what orders of magnitude do we have here. So for example, suppose it's an electron. So BL was what? B is 2 square root of mu divided by h bar. Square root of V0 minus E, and then everything multiplied by L, right? So h bar is kind of the order of 10 to minus 34. The mass of the electron is more or less 10 to minus 30. The kind of energies typically used here are of the order of 1 electron volt, which is in international system going to be 10 to minus 19. So this is joules, this is kilograms, this is whatever, I don't remember. And then we have this L here, which we can change, right? So we can change this from millimeters to nanometers to whatnot, depending just on our lab settings. So in fact, we have quite some freedom of whether to make this number very small or very large, just depending on the size of the barrier. So for very narrow barrier, so narrow, then turns out that you can be more or less in this region. You can make this thing very, very, very small. So T is going to be more or less 1. Yeah? I'm not even giving you the exact form. And this is what we call tunneling, right? So which doesn't happen classically at all. It's like incoming particle, outcoming particle. It's almost as if it has not seen the barrier, which doesn't happen classically, right? If you go against the wall, it doesn't matter how narrow the wall is. If it's taller than you, you don't go past it. It doesn't happen with classical particles. So if BL is now, if we make this large, for example, by making the barrier large, then T is going to, okay, T is going to depend on E2 minus B L times 2. So it decreases exponentially with the barrier size. Here, there's some coefficients here behind, which depend on V and E and so on. But then it's really like the wider the barrier is, the fewer particles you get on the other side, or the lower the probability of finding a particle on the other side. Yeah. Okay, but T will still decrease kind of monotonically with this thing inside here, BL. Nothing too strange happens apart from the fact of like of having a particle crossing walls. And I was looking for examples of tunneling that might be relevant. Apparently, in the enzyme that processes alcohol in your body, there is proton tunneling. So there's protons tunneling. So this was a statement by a quantum chemist, which we will eventually invite to give a lecture at some point, maybe next year, so that he can explain us why this is the case. Okay, so let's go for a break now. Oh, sorry, you could have told me something. Let's take 15 minutes, yeah. So we restart at, let's take 13 minutes. Yeah, then let's start at 20 past. Complaining. Okay. So now we're still in the case of the square barrier, but we're going to look at a case where the energy is now higher than this B0. And that's where we see something kind of funny. Resonant scattering, and we'll tell you why. So this is the case E larger than B0. So here's the energy of the particle. Here's my B0 is smaller than this. Yes, it's exactly the same setting. I just send out, well, I prepare or I just look at the energy eigenstates of particles with more energy. So one option is to just send an electron with more energy and see what happens. So now, well, it looks the same, right? So again, for now, we just use the, oh, I'll tell you in a bit. Outside, we have this, this incoming reflected and transmitted waves with the same K because they have the same potential. And inside, there's also there is also a wave of this form. It just has a different K that is smaller because of this difference here. So let me just write here. General case X, which is A, KX, must be E minus X. I'm just going to call the K in the middle K prime. X is here F plus G okay. And again, we don't worry about the A because this is given by the normalization. And we look, we're going to have 4 equations for 5 variables. So you can set this one to 0 for free. We could also look at cases where we set one of the others to 0 for free. Okay. But we look at this. And again, we have 2 points. In each point, we have 2 conditions. So you're going to get 4 conditions for 4 variables now, right? B, C, D, and F. I'll write them down for the sake of completeness. Okay, so at x equals 0. X equals L. So from the first one, we get that 1 plus b equals c plus d, like before. From the second one, now we get ak 1 minus b prime minus d. Here we need to group this two. So we get c I, k prime l is d e k prime l equals f k l. And here we take the first derivative of this two. Okay, f. Okay. They're a bit annoying, but it's again four conditions for four variables. So we can solve them, which you can do if you want. But let's look again at the transmission coefficient. And this is where it starts getting funny because, so remember t in this case, it's given, so t minus 1 over t is given by 1 plus 0 square. So these don't change. And then you have inside here sine square of a prime L. Yep. And the reason for that is because some of the I coefficients here cancel each other out, which before didn't. So where before you had a hyperbolic sign, now you have the normal sign. That's essentially it. So if you have x and sine square of x, well, this is 1, this is 0, pi, and so on. So now the transmission coefficient no longer is monotonic. Does not just grow with like the distance or k. In fact, instead it has this oscillating behavior. So now let's look at it a little bit more, a bit closer. To see what's happening here. So to be honest, I don't know if people first did the experiment and found out this funny phenomena and then look at the maths, or if they first really worked out all these coefficients and saw that something funny was happening to the transmission coefficient. But it's something that is extremely useful. So first, let's look for KL is smaller than 1. This is again a very narrow barrier. Well, here in this is like very close to the beginning of the x-axis. There's like sine of x is approximately x. You know, so which in this case is very, very small. So your t is going to be approximately 1 plus a linear factor, right? So t is going to be 1, or t minus 1 is 1 plus some constant times x. But t is very close to 1. Yeah, that's a narrow barrier. It's just like before, it's like you didn't see it. But if it's no longer a narrow barrier, so if you have k L larger than 1, then still at those points where the sign is 0, then the whole second half of the quotient term is 0, so t is 1. So when theta equals n pi, then sine square of k per L 0, so t is 1. Okay. And when this happened, so now we need to replace what k prime was. So we have n pi equals k. What is k? Is square root of 2 mu of h bar. And now e minus v0. And now L. And now if we solve this in a different way and just write it in function of e minus v0, what we get is e minus v0 is, oh, there was a typo in the lectures, by the way, but it's solved here. N square. And now this should be familiar for you, because these are the energy, this thing on the right, these are the energy eigenvalues of the particle in the box, right? So E minus V0 is the thing we did at the beginning of last week. In a box, which corresponded to what? So now if you solve this in order to K, it will correspond exactly to inside this hill. So we have the box, and it corresponds to your n equals 1 being this, your n equals 2 being this, and the n equals 3 being that, right? And then we have the incoming and the transmitted. So wait, what does this mean? That when the energy of my particle is such that that it would correspond to like these energy eigenstates of a particle in a box, so it fits really well. So the wavelength in here really fits well the length of the box, like the guitar strings. Then the whole wave function is transmitted, right, for the energy states. When it's not exactly this, then it oscillates. So it looks a bit like this. So if I'm plotting t, so a transmission coefficient as a function of E. So the maximum is going to be 1. So for E smaller than V0 is what we saw before. It was the case we did in the first half. So it would go something like this. And now it comes there and it goes down. And it comes there. Oh, let me do it a bit narrower. Comes there and it goes down. And it doesn't go down as much now. And it comes here. And it comes there. And eventually it will saturate because eventually we'll get to this setting here where the energy of the particle is just much, much bigger than the box. So it's like, it almost doesn't see it, right? But there's this region here, this sweet spot where you have these resonance peaks. And this is the same idea as like resonance classical waves, right? Is really, it looks like a stationary state. The wavelength really fits well inside the box. So how can we use this? First of all, this has no classical equivalent. I mean, I just said it did, but not in the setting of shooting a particle through over a barrier. So this can be used in many ways. So for example, if you can control the energy of your particle very well, and you shoot many, and then you see at what point, at what like points do you see, you put a detector here, at what points do you see most of them coming? So you can work out these points. Then you can learn, for example, L, right? Or you can learn V0 if you know L very well. So this is used a lot to characterize materials, right? So for example, maybe I'm shooting protons and there's an atom here, so they fill this, or an ion here, so they fill this atom as like a little barrier, maybe not exactly square, but approximately squared. They still have more energy than this, but still there's some probability of being reflected. So I can learn something about the effective radius of this atom here. In general, it's used in metrology. Not meteorology, but metrology, which is about measuring distances using quantum systems. So if you want to measure like how thin your like nano pellicula or little wall that you built is in a circuit, then you can use this method to very accurately measure this length L. So that was kind of it. Are there questions at this point? There should be, yes. No.
So where is it in the graph?
The K prime?
Yeah.
Yeah, so the K prime is the thing in the middle. So sorry. So the K prime is here. I didn't want to write it down the whole time, but so K is square root of 2 mu E of h bar. So it's the momentum outside the box, and K prime is 2 mu, no, E minus V0. Yeah. Okay. All right. So okay, there's another case that we have not seen yet, which I'll do. I think I'll do this in the lecture that I will just upload online sometime this week, which is the square well. It's going to be the opposite. So now we have Shook, and the potential goes down in a finite region. So it's like the finite case of our particle in a box. And we look here again, what happens if the energy is larger than this? It will still fill this dip. And what happens if the energy is lower? Yep. I mean, in this case, I guess you could also look at what happened if the energy. No, you can't. It's not possible. Okay, so this one, again, you could solve it exactly in the same way, but there is actually a nice trick one can apply. So I will do that in the online version. Good. We will look at the 3D case later after we talked about spin and rotation. So now we have 10 minutes, and the question is, do I start spin? Yeah, I can start spin. Oh, no, I have 10 minutes. I'll just talk about something I want. Much better. So every now and then it's good to remind ourselves of what is the limit of the theory that we're using. Okay. So first of all, no physical theory that is useful is completely self-consistent in all regimes. Even electromagnetism, even in classical regimes, there's some problems that you can come up with, some settings where the theory gives silly results. And again, it's just like this wave and particle distinction. Use them in a regime where they're useful, not don't take it as like God-given in any way. So one of the things that you might have heard about is that quantum mechanics and special relativity don't fit very well. So there's a whole field of quantum gravity where people try to connect the two things. One of the reasons why we cannot just apply quantum mechanics in that sense is that time is relative to the reference frame in general. So remember, when we derived the Schrödinger equation, we started from the beginning by saying that we had this uniform dynamics, which meant that we had some parameter t, such that u of t2 t1 was just the u of the difference, right? And then we saw two examples. One was when this t was the rotation angle or something, and then from then on, it was always time, right? So keep in mind that this is the condition for which we can apply what we've been done for the second half of the semester so far, right? Something that if you take, for example, after this lecture, you can take QM2, which Renato Renner will give this semester. And you will start precisely by taking the case where we cannot expect things to evolve linearly in time. And in fact, we need to take out kind of a time-independent reference frame and look at space-time as a whole. Right. In that setting, then, you know, like if you think of, well, this is our reference frame. Like we're sitting here, we see space in these dimensions, and we see time go up linearly. But we can pick by moving in a, being close to some very high gravitational mass, or moving with some acceleration, different 2 hours, we can choose an observer that would have a different x and t, right? So meaning that like their view of space-time, they don't connect directly their time to our time. You need to take time and space into account to relate the two. Meaning that to then translate what is Schrödinger equation or what is physical evolution according to Schrödinger equation in our reference frame to the view of this person who is in a spaceship accelerating or close to a black hole or so on, then you cannot work in this scenario. You cannot make these assumptions, right? And then you need to take a time-independent view of quantum mechanics, which has some other problems which are not yet totally solved. Yep. So that's one takeaway message I wanted to give you at some point. So today is a good day. Good. Can I give you more things? No, I will not give you more things. We'll start with spin on Thursday. And I might start the class a bit early, like 10 minutes early, because we're always just sitting there waiting. Yep. All right. Yes?
Example, you look for from one to the other, or is it more complex than that?
Yeah, it's a bit more complex than that, right? Because we did all, you know, if you're just transforming a static state on a Hilbert space, yeah, even that is a bit harder. So it's a transform at a higher level, because everything we did so far always assumes that time is this classical variable, right? Time is just this thing that we can count, and we can describe our evolution in terms of, which is, it's not how things work, right? I mean, in reality, we don't even ever measure time directly. What we measure is clocks, which is the evolution of a physical system. So what one can do is then to try to relate like a quantum clock that a person here has to a quantum clock that someone there has. And that is, yeah, that is quite cool. And I hope if you took this course and then quantum mechanics 2 in the next semester and advanced topics for QIT, you probably already will have most of the tools needed to do that. I mean, as far as anyone has them. Yes, yes.
How accurate are all our stuff we're doing? Because we're not taking account relativity, right?
Yes, exactly, yes. So
is it useful that much? I mean, I guess in some.
It's totally useful if you're doing experiments on Earth in the lab. Yes, so this we can verify to very, very high precision. So for example, one thing that people are very excited about in foundations is that as we can do, we have more and more quantum control, right? So we can already have superpositions of a tiny electron being on the left and on the right. But ideally, one day we'll want to have like a superposition of having a big mass on the left plus having a big mass on the right. This is extremely hard to arrange, right? You need very, very good control, but we're getting there. So why would this be interesting? Well, because general relativity tells us that the passage of time depends on how close you are to massive particles, right? So, you know, if you've seen Interstellar, time goes slower if you're closer to a black hole, right? So this means that you could have really a superposition of, for someone here doing an of having time going faster and time going slower, for example. This can even lead to experiments we can already, so we can already design in theory experiments that we could do if we manage to have this superposition of like masses big enough, like it should have to be really, really massive, or we have to have very, very good instruments to measure the passage of time at one of the two. Of what happens if you can have like a superposition of 2 times of space-time, right? The space-time that is kind of induced space-time by this geometry and by this geometry, right? And this can lead to, I don't know, the causal structure of this thing, like whether something happening here versus something happening here, which one is in the past and in the future, can depend on these two things. Okay? So this would be very, very exciting when we can do this, because then we can actually use this to even test different interpretations of quantum theory or different predictions of what happens if you have the superposition of causal structures. Yeah. So anyway, this is some of the research that is fun. And in the quantum information theory group, we care about these things just at a theoretical level. Yeah. From this to quantum clocks to thermodynamics of this kind of systems and so on. That's all fun. Okay, so I'll let you go with this. Let me just turn off the streaming. Oh.